So, um, you are all welcome. Today's presentation, as mentioned by the chairman, it's going to be the first lecture on a course, Introduction to Homological Algebras. This lecture is going to talk about preliminaries and category theory. And as we have pointed out, the material for this course will be an introduction to homological algebras by Joseph J. Rotman. And most of the content of these slides are taken directly from that textbook. So even though the the course is on homological algebras, but we need to talk about category theory because of the fact that categories are a suitable framework in which homological algebras can be discussed. So the motivation to studying category is in the fact that most of the algebra consists of study of sets with a given structure. See, when you are looking at many algebraic objects, you will discover that you are dealing with a set with some binary operation defined on the set. And then in the study of algebraic structures, we also tend to look at mappings preserving this structure. And for example, when one is studying groups, we look at group homomorphism as the structure preserving maps between groups. And if you are looking at ring and the study of rings, we also, alongside the rings, study ring homomorphisms to serve as the structure preserving maps. And these are the entities that led to the realization of which ring or which groups are the same. And then vector spaces also is another algebraic object that is studied alongside its structure preserving mappings, which is linear transformation. And then we also look at topological spaces alongside with the continuous mappings. And this gives us a realization of when two topological spaces are homeomorphic. That is, they are the same as far as the topological properties are concerned. So this is the motivation. When you look at when you look at most of the algebraic study, you are dealing with sets along with mappings between the sets that to preserve the structure of that mathematical system. And then the most interesting aspect is that there is a framework, a general framework that one can look at for studying these structures so that you tend to generalize the entirety of the theories in one place. So we have a general setting where we can study all of these structures. And this setting, this general setting is actually the category, and it was S. Ellenberg and S. MacLean that introduced the basic concept in 1945 uh, of what is now called categories and functors. Functors will be mappings between categories, and we will look at what these things are in our lectures. So actually, it is this category that we are going to first look at because they will serve as basic settings where we can talk about homological algebras. So categories are actually the context for discussing general properties of systems such as groups, rings, vector spaces, modules, sets, topological spaces, alongside with their respective transformation. So mostly when you are looking at group, we have seen example, you look at also group homomorphism, rings along with the ring homomorphism. vector spaces with the linear transformation, and modules with R homomorphisms, that is module homomorphism. And when you are studying sets, you also want to look at mappings between set or functions between sets. And this will serve as the structure preserve, because if you look at a plain set, it doesn't have any structure. And so any map you take between any two sets will serve as a structure preserving map. And when you are looking at topological spaces, the mapping will be continuous mappings, and likewise there are many other mathematical systems that one can look at. Their study is being done alongside with their respective structure preserving transformation. So category theory is actually a generalization of all this. So it's a general setting where one is studying an abstraction of groups, rings, vector spaces, modules, and so on. So while topological spaces, measure spaces, groups, rings, and vector spaces are considered to be abstract algebraic objects, there is even more abstract setting in the name of category that generalizes all of these things. And once you understand category very well, you have a very good framework and a language in which you can interpret most of these theories. So we are going to go through this starting from the very definition of what category is, and then move into the theory and try to see that we introduce that part of the theory of categories that we need for better understanding of homological algebras. So we start from the very beginning with the definition of category. So a category, which we donate by C, call it letter C, consists of three ingredients. So you think of a category as a bag containing three things. So you must have three items inside the bag, that container. So it is a container consisting of three items, and the items are a class, obj of C. So the class, uh, the element of this class are called objects. So this is a class of objects. The members are called objects. And when we say class here, it doesn't have to be a set, because in classical set theory, it's not every collection that is a set. We have seen Russell's paradox, where he tried to actually, in considering the collection of all sets, it is not a set, because if you try to get hold of all sets and form that collection, it's stop at the level of being a proper class. It is not a set. So we don't require this collection of objects to be a set always. So what all that we require is we should have a class of objects. So elements of this class or members of this class are called objects. So examples will actually make these things clear. And then the second entity that you want to have in the container, which you call category, is that corresponding to each pair of objects coming from the class of objects, there should be a set which we donate by hom AB. And the element of this set are called morphisms. And then think of them like mappings between the object. So this object, you can think of them like sets, and then there is collection of maps between the any two sets. And then the third item in the container, which we call category, is to have a composition law, such that for any three objects in the category, we shall find that there should be a law, a composition law, that we can compose any three such objects. So if you have an object from A to B and another object from B to C, then there should be a composition law that you can combine these two morphisms. If you have a morphism from A to B, sorry, I was saying object morphism from A to B, and another morphism from the object B to C, then you should have a way of composing the two morphisms so that the product, actually the result of the composition should be another morphism from A to C. So that composition law must be available in the container so that you should know how to compose morphisms. So this is actually, these are the three ingredients of a category. But then these ingredients are subject to the following axioms. So they must satisfy these three axioms. The first axiom is that no two home sets. This set is called home set. So set of morphisms. So no two set of morphisms are intersecting. So intersection of any two set of morphisms should be empty, unless if C and A are the same and B and D are the same. So actually you think of this as a map. If you have an element here, it is a mapping from A to B, and an element here should be a map from, think of it as a map from C to D. Then if there is intersection, you are saying that a particular mapping, one single mapping, is having two different domains and two different codomain, and that is not allowed in the definition of a category. So this particular axiom is to say that every morphism is having a unique source, which is the domain, and a unique target, which is the codomain. So the domain is called the source. This is the general name. The codomain is called the target. So we understood what domain and codomain are from the classical set theory. Now, the second requirement, property that these items should satisfy, is that the composition law here, coming from the container, should be associative. So if you take any F morphism from A to B, and another morphism G from B to C, and another morphism H from C to D, you see the way you pick these morphisms is in such a way that the composition HGF is defined, because the target of F is the source of G, and this target of G is the source of H. And so therefore I can do the composition. So both of the compositions are defined. So, and whenever any the two composites are defined, they must be the same. They must be equal. This composite HGF must be the same as HG, then F. So this must actually coincide. In other words, you are saying that the composition law must be associative. And then the final requirement for the definition of a category is that for any object, there should be an identity morphism. So there must be an identity morphism corresponding to every object A in the category. And the identity morphism should be a morphism from A to A, such that if you take any other morphism F from A to B, F after 1A, that identity morphism should be F. And the 1B, that is the identity morphism corresponding to B, when you compose it with F, that should be equal to F. So actually, this is the three requirements, and the definition of a category is very simple, in such a way that you only need these three entities and satisfying three requirements here. And this generalizes all, capture all the properties of a set, along with the mapping, preserving the structure of that particular system. One point that I would like to emphasize here is the way we write our composition. The composition law, look at the way we write it. Actually, you have F is coming from AB, and G is coming from BC. But then when we compose, we write GF. So it's better, the way I understand this is to say G after F, because you start applying F, F should be from A to B, and then G is from B to C. So the end result should be from A to C. So this composite is actually G after F. So you apply F first and then G. So this is how we should understand it. So not to get confused with the notation, so that this should be understood. Because if you look at this one now, you have to start applying the identity morphism. It is one A, which is now from A to A, and then F apply from A to B. So you see that if you start by applying the identity and then F, you end up having F. And if you have the identity on B, uh, and you apply F first, so you see A to B, and then next identity on B should be from B to B, that should produce F again. So this identity morphism are satisfying these properties. So this is actually the definition of a category, and we will now try to give so many examples, and these examples are not just for exemplification purpose. We want to give the examples that we may be using subsequently. So the examples are introduced along with the uh, terminologies and the notations which we are going to be using subsequently throughout the course. So but then I want to also clarify this issue of a notational issue here, which we may likely be using. For example, these morphisms, we say we think of them as functions from A to B. So if you have a morphism in the home set of AB, you see it is a morphism from A to B. So what we normally do in the notation is to write, because this is so cumbersome, and it's easier to have one line notation, to just write F A to B, just like a map. Even though we see examples that not all morphisms are mappings. Sometimes morphisms are just points, they are not mappings. So, but we can always think of a morphism as a map from A to B, given the classical example that morphisms are a generalization of functions between sets. Or most of the time, instead of writing F such F a map from A to B, we write F to AFP. And so here you are thinking of A and B as vertices, and then F is a labeled arrow starting from A to B. So you see, it's again think of as a mapping from A to B, and that is why sometimes they are called arrows. And in that notation, we normally refer to morphisms as arrow. We just call them arrows. And so therefore, a morphism is also called an arrow. So sometimes you will be saying, let F be an arrow from A to B, or consider an arrow, and by that we are referring to a morphism. So that should be clear from this point. Now, if you have a very clear context where you don't have to always spell out which category you are in, if the category is clear from the context, instead of writing home with a subscript C to pronounce the morphism, we'll always just write home AB without having to mention the category actually. So you don't need to always talk about mention the category here. You can just uh, say home of AB when the context is clear. In other words, if you understand which category you are working with. Are you with me? Okay. So um, I now present a number of examples of what we call the category. The first of our example is sets. This category, the object in this category are all sets. And then the morphisms, because we say we must have objects, and then we take the collection of all sets. So this is a class, it's not a set. We take the collection of all sets as our object. So every set is an object in this category. And so you can talk about mappings between sets. So therefore, if you take any two such sets or objects, the set of mappings between them, or the morphisms, will be all mappings from A to B. So this form a category because we know we have a composition law. We have a composition law, and the composition law is associative, and there is always the identity mapping from A to B, and the identity mapping is satisfying those requirements stated in the definition. And then the second example is groups. Groups, this object in the category groups are all groups. So if you take the collection of all groups, it forms a category. And then morphisms here are group homomorphisms. So one can easily check that because when you are dealing with group homomorphism, you have mappings. There are mappings, and you have composition of mappings, and the properties are also satisfied. And then you can also take the collection of all abelian groups to form the object in a category which we call AB. So all abelian groups, and then all group homomorphism between any two abelian groups will form the morphisms. And then you can also take the category rings. Rings is a category whose object are all rings, and then morphisms are ring homomorphism. So we can now see that the abstract of algebraic object we know of sets, group, abelian group, rings, and even commutative rings, they are just falling out as examples of this concept which we have just defined called category. So there, the fifth example is com rings. This com rings is the category of all commutative rings, and the morphisms in that ring are ring homomorphisms between commutative rings. And then we have the category of semigroups, and morphisms there are all semigroup homomorphism. And we also have the category of monoids, where morphisms are all monoid homomorphisms between semigroup. There is difference between semigroup homomorphism and monoid homomorphism. In defining a monoid homomorphism, we will have an additional requirement that the identities must be mapped to each other. So the identity in A must be mapped to the identity in B. And so therefore, not every semigroup homomorphism is a monoid homomorphism, but every monoid homomorphism is also a semigroup homomorphism. So that distinction should be made actually clear. And then we can have a category which we call vect F. So vect F is a category. Can you hear me? The people online, can you hear me?
Yes, sir. Yes, sir. We
Okay,
can hear you, sir.
thank you very much.
Yes, sir. We can hear you.
Okay, okay, no problem.
Yes, we
So
can hear you very well.
okay, vect F is a category actually whose objects are all vector spaces over F. And the morphisms here are linear transformation. So associated with any two vector spaces, you assign a set whose elements are all linear transformation between the two vector spaces. And then you can also have an example of a category in which all the objects are topological spaces, and there the mappings or preserving the operation will be continuous map between topological spaces. So A and B here are topological spaces because we are in the category of topological spaces. So you can now see from the example 1 to the ninth example, all here we are given examples of categories where the object are sets, and also morphisms are mappings. But we can still have categories where objects are not necessarily sets and the morphisms are not necessarily mappings. So, and this is the example 10, the content of example 10. If you have a partially ordered set, and this is a set where the together with a partial order, that is a reflexive, antisymmetric, and transitive binary relation defined on the set. So for given any partially ordered set, you can define a category po of X by choosing X to be your object set. The set of the collection X of objects is now the set X. So which means your objects are just the point inside that set. So they are not necessarily set here. You can just take for example, the set of natural numbers under the natural partial order of the natural numbers, and you would see that objects in that category are just natural numbers. or you can take any partially ordered set whatsoever. So if you have any set with a partial order, you can regard the element of a partially ordered set as objects. And then how do you define morphisms now between any two objects or point in the partially ordered set? So if you take any x and y in X, which are noun objects, then you assign to that to that pair XY a home set defined in this way. If the pairs, if X is less or equal to Y, then you say if X is not less than or equal to Y, then you declare the home set to be empty. Otherwise, it should consist of a single element associated with x and y. So, and we label the element xy, kappa xy, in order to signify that this is the singleton set, or this is the single element, a unique element inside the home set in the situation where x is less or equal to y. So actually, this is just a symbol, it's just a label. So what we are saying here, whenever x is less than or equal to y, the home set is singleton consisted of only one morphism. And this morphism is actually not a mapping because these things are even points. So it's just an arrow between x to y. So there is always an arrow from x to y if x is less than or equal to y. And there is no arrow from x to y if x is not less than or equal to y. This is, in other words, what we achieve. So you see, these are not mappings actually. And composition in this category is given by this law. So if you take any point or any morphism from x to y, and you take any morphism from y to z, so you see the source of this morphism is x and the target is y, while the source of the second morphism is y. So once the target and the source are the same, you can compose. So the composition now of this with that should be, so the composition x, y, y, z should be xz. And this composition makes sense because if you have an arrow from x to y and an arrow from y to z, then you have an arrow from x to z. And this is always the case because you are working in a partially ordered set, because your relation is transitive. So this is a transitive relation. So if x is less than y and y is less than x, then x will be less than z. And y is less than z, then x will be less than z actually. So by transitivity, this composition law makes sense. And it is clear that corresponding to every object, if you take any set x, any x from the object set, there is always, because x is always less than or equal to x by reflexivity. And so therefore there will be kappa xx. And that kappa xx will be the unique element inside there, and it will play the role of identity. And so that is the identity morphism defined, associated with every x, and it is the only morphism associated with x. And so there is always an arrow, a loop from x to x, and this is following by reflexivity. And if you take this loop and compose with any other point or morphism or any other arrow, you definitely get the arrow back. And so therefore, this is a category defined in this way, and it is generally defined taking any arbitrary partially ordered set. So which means if we specialize the cases of this x, we can come up with so many definitions of categories associated with partially ordered set. For example, if you take x to be the set 0 to n minus 1 for any natural number n, and then you take x to be the set 0 to n minus 1 and give it the natural partial order. In other words, 0 is less than 1, less than 2, the usual order of the natural number. So if you look at this one as a partially ordered set, then we have a pole of n. This is a partial, this is a category actually. So we have this category, and then the definition is the same thing. So which means this category has as its object 0, 1, 2, 3 up to n minus 1. And then there will be an arrow from 0 to 1 because 0 is less than or equal to 1. So you have an arrow, and there is an arrow from 1 to 2, like that. And then we have not actually drawn all of the arrows, because there will be also arrow from 0 to 2, an arrow from 0 to 3, an arrow from 0 to up to n minus 1, because 0 is less than or equal to all the elements inside there. And then likewise, there will be arrow from 1 to 2, to 1 to 3, 1 to 4, and so on. So this is but these are the basic arrows. All the other arrows can be obtained by composing, because if I compose this arrow from 0 to 1, composition the arrow from 1 to 2, I will get the arrow from 0 to 2. So that is why we are revealing this arrow serves as the generators. So, and then we'll talk about diagram later on. And then the category po of tau. So you see, you can take always a topological space and then give the topology of the topological space a partial or partially ordered set structure, the set structure of a partially ordered set. You can give it the set structure of a partially set by set inclusion, because element of a topology are subsets of X. So some of the subset are subset of some other ones. You see some subset are contained inside some. So if an open set here is contained in some other open set, you say it is less than or equal to it. So if you take the usual set inclusion, this is a partially ordered set. So therefore, you can take your set here in this example to be tau, so that you have po of tau. So this is a category actually. So which means associated with any topological space, I have a category whose objects are open sets. And then the morphisms are the singletons, the arrows between the open set, where there will be an arrow from an open set A to another open set B in the event where A is contained inside B. So this is how you should you can get this particular category. So this is the number 11 and number 12 are just special instances of the example number 10. Example number 10 is very general, and then this actually number 12, this poset arising from the defining a partial order of inclusion on a topology of a topological space. This particular poset will play a fundamental role later on in our theory of shapes. And then we have this actually category where we can define a partial order on the set of integers by n is less than or equal to n minus 1. So this less than or equal to, this is the reverse order, because the usual order is n is less than or equal to n minus 1 is less or equal to n. But then you are reversing all the orders. So anything that is less, you now reverse it to be the bigger one. So this is the usual, the reverse order of the usual order of the natural integers. And then with this is a partial order, because this order is reflexive, antisymmetric, and actually transitive. So you have a partially ordered set. So you can give the set of integers the structure of a partially ordered set by defining a reverse order in this way. And so with that, if in example 10 here, you choose that reverse order here, and you take X to be the set of integers, you have a category. So this category is denoted PO of Z. So, and then we are going to also talk about this category later on. So we have this category. This is another example of a category arising from our general example presented in 10. And then there's another construction, a general construction of a category, where you can construct a category by taking a monoid. And we know what a monoid is. It's a semi-group with identity. So if you take a monoid, you can define a category on a monoid by as follows. So the category is denoted CM, and then object in that category will be star. So the binary operation of the actually monoid. So the object is the binary operation of the monoid. So you see, it has only one object, star. So you don't have many objects. This is just a singleton set, star. That's the object of the category. And so therefore, you can only have one home set. So you can only have morphism from star to star. And how do you define morphism from star star? So it is to take M, the entire monoid, underlying set of the monoid. So which means morphisms are now element of the monoid. And then the binary operation is the object. So you can see that this example is actually preparing your mind or drawing your attention into uh, thinking in a right way. Don't think of morphisms always as mappings, and don't always think of object as sets. This concept of category is more general than your initial thought of it, because initially it was a generalization of sets, groups, rings, fields, and so on. And all these ones are actually um, sets with mappings. But when we try to get hold of a common property of all of these settings that are set and mapping, and we come up with a more general definition that take care of all of them, so that all of them are now falling as example, we discover that in that universe where they are coming as an example, there are other entities where the objects are not even sets and the morphisms are also not mappings. So therefore, I think when you abstract, when you tend to generalize a theory or you make it abstract, you tend to actually enlarge the universe to even see what you never thought will fall as an example of what you are dealing with. And that actually open up a whole new area and more interesting concept, even in application. And so you take the home sets. So there is only one object, so you can only talk about the home from star to star. So what are the arrows from star to star? They are element of M. So so morphisms are element of M. And then how do you now compose? The composition law should be, so if I take any morphism here, it is an element of the monoid, and take another morphism which is another element of the monoid. In other words, I have a G and a H, then I can compose them, and the composition should be G star H. In other words, I should just do the composition of the binary operation of the monoid. So the composition law is just the binary operation of the monoid. So the usual multiplication of the monoid will be the composition. So, and this construction, we are going to actually utilize it in the theory very well. So actually these examples are not just there. We will make reference to most of these examples. So having clarified the fact that the notion of category is not null and void, because so it is actually a genuine generalization of the concept, we can see that there are all what we have looked at, the semi-group, the rings, the monoid, the groups, they are all example of category. And apart from being example, those being example, we have other categories that do not look anything like these algebraic structures we dealt with before. And so therefore it means this is a very serious concept and we can study it. So most of this discussion will be surrounded by too many examples. Hardly we can even present any proof, because we are just introducing the concept. So we will have to present all the definitions and most of and the examples before we start talking about results. So there is the notion of small, large, and discrete categories. So some categories are small, and some of them are large, and some are discrete. So a category C is said to be small if the set of objects is a set. What does that mean? So you see here, when we talk about sets, the collection of all sets from classical set theory, we know that this is not a set. From the Russell's paradox, you cannot take the collection of all sets. So if you take the collection of all sets, it's not a set, it is just a proper class. So this category set is not a small category, it's a very large category actually. In fact, we say a category is large otherwise if the collection of object is not a set. And but if you take object, look at this category here, at our disposal. Object CM, it has only one singleton. This is a set. So this is a small category. And this one too is a small category because object here is just the set of integers. So it's a set. So it's a small category. So those are called small categories. And then a category is said to be discrete if the only morphisms in that category are the identity morphisms. So given any, sorry, there is a typo here, I will correct it. We say a category is discrete if the only morphisms are the identities. And that is for any two objects. The set of morphism is either empty or containing only the identity morphism. So please, this A and B should be X and Y. So that, or here it should have been X, A, and then A equal to B. So this X here should be A, so that I have the identity on A, and then if A equal to B. So if A is equal to B, you have a singleton set consisting of the identity morphism. And if A is not B, it will be empty. So you don't have any other morphism in the category except the identity morphisms. And such type of categories are called discrete. This is the notion of a discrete category. And then we talk about subcategory. This is actually always what we do in algebraic study. Once we define a concept, we say sub. Set, subset. Group, subgroup. Ring, subring. Vector space, we say subspaces. Topological space, we talk about subtopological space, and so on and so forth. So therefore, we can also define what the notion of subcategory, because we can see that some categories are contained inside some. So a category S is a subcategory of some other category C. So S is a subcategory of the category C if all objects in S are also object in C. So the class of object is contained in the class of object of C. So all the objects are picked from the object of C. And then for any two object A and B, the home sets. So all morphisms in S from A to B are also morphisms in C from A to B. And then if F is a morphism from A to B, but in the category S, and G is also a morphism from B to C, but in the category, no, this should be in the category S, this should be S. So if G is also a morphism from B to C, but in the category S, then the composite GF, you see, so because you have the same source as the target here, so you can compose F and G. So the composite G of GF, or G after F, will now be a new morphism from A to C in the category S. Remember, I said this thing is also, this C here should be S. So you are working in S. And so because of the property 2, the condition 2, F is also a morphism in C, because all morphisms in S are also morphism in C by this property. So therefore, you can compose within the smaller category, and as well as you can also compose within the larger category. So what we are saying is that the composite in the smaller category must be the same as the composite in the larger category. This must hold. And whenever you take any object, the identity associated with that object in the smaller category S must be the same thing as the identity in the larger category. So these four conditions are what are required for the definition of subcategory. So a subcategory must be a category that satisfies these four conditions. And then a subcategory is called full if instead of condition 2 here, you see the condition 2 here, the only requirement is that the home set, all morphisms in S are also morphisms in C. Now, if here instead of inclusion equality hold, that every morphism in the category is also a morphism in the subcategory, then the subcategory is called a full subcategory. It means it consists of all morphisms between the uh, objects, between any two objects. So for example, if you look at the category of abelian groups is a full subcategory of the category of groups. Because if you are in the category of groups, when you look at any two abelian groups in the category of groups, morphisms are group homomorphisms. But this group homomorphism, they are still the group homomorphism in the category of abelian group. So therefore, all the morphisms here are also found in here. So so therefore it means it's a full subcategory. But then we know that the object is contained inside, and you can easily check that all these four properties are satisfied. And groups also is a full subcategory of monoid, because every monoid homomorphism is also a group homomorphism. Yeah, every monoid homomorphism. Actually, what I want to say here is, if you take any two monoids that are also groups, then every monoid homomorphism between them is already a group homomorphism. So every monoid homomorphism between two groups must also be a group homomorphism, and so therefore this is a full subcategory. But monoid is a subcategory of the group of the category semi-groups, and this is not full, because you can take two monoid in the set of all semi-groups, but the semi-group homomorphism between them is not monoid homomorphism. You can have two monoids A and B, and a semi-group homomorphism from A to B that do not that may not necessarily fix the identities. So identity in A may not map to the identity in B when you are dealing with semi-group homomorphism, and so therefore it will not be a monoid homomorphism. So this is an example of a category that is a subcategory of the of some other category, but it's not full. So not every subcategory is full. For example, if you take the category of groups, it's a subcategory of sets, but it's also not full, because if you are in sets, you don't see any structure. So all groups are also members in sets. So all object here are also object here, but not every mapping between two groups is a group homomorphism. So therefore, morphisms are not the same here. You see, but every morphism here is already a mapping, so you find it to be a morphism inside here. So therefore, this is the notion of subcategory and also full subcategory. So we also define the concept of opposite category. It's another construction that give rise to a new category out of a given one. You can construct a new category out of a given category. And how do you do it? Is just by reversing all arrows. So the only is easy to define. You have a category, and the opposite category of the given category we denoted by C op is just the category whose object are the same as object of C. So just the same object set or class. But then morphisms in the opposite are the reverse of the morphism. So you just reverse all the arrows. If you have any arrow from A to B, you replace it by an arrow from B to A. And that is all you do. So you reverse the direction of all arrows. If you have a morphism F from A to B, you just reverse the order. It becomes a morphism from B to A. And then in that way, you obtain a new category, which is called the opposite of the original category. And then composition law is also defined in the reverse. It's actually just the reverse of the composition in C. So in other words, the composite G opposite after F opposite should just be the opposite of FG. So which means compose them inside C, compose the reverse inside C, and take the opposite, and then you are there. You get a composite. So this is how you do the composition, and then it's an easy exercise to check that this is actually a category. In other words, it satisfies the three requirements that the composition here is associative, and if you take the opposite of the identity, is still the identity, and then the identity is also having the same type of properties. And then we define the notion of isomorphism. So when is a morphism said to be an isomorphism? So a morphism, so in a category, is called an isomorphism, and then think of morphism as maps, but remember they are not mappings always. They are not always mappings. Just call them arrows. You have A to B, an arrow, F. So in a category, it's an isomorphism. So this generalization of the concept we know. So in fact, you can call a point an isomorphism, not necessarily a mapping here. If you are in a category where the, for example, that category here, this particular category, where morphisms are element of the monoid. So like you take the set of natural numbers. And so morphisms are now numbers 1, 2, 3, 4, 5. Because if you take the set of natural numbers and the multiplication is a monoid, and then the object and is now multiplication is the object. So you can see that you are now calling a natural number an isomorphism. And how would that, so you can see you are generalizing your ideas, all the knowledge we are trying to generalize, the knowledge you have in your head about certain terminologies when we say an isomorphism. So a morphism in a category C is an isomorphism if there exists another morphism from B to A. So this morphism is from A to B, but then if there exists another morphism from B to A, and this morphism from B to A is called the inverse of F, such that the composite G after F is 1A and F after G is 1B. So actually, if this happens, then we say F is an isomorphism. And likewise, F will play the role of the inverse of G, and it is an isomorphism. So in defining an isomorphism, these are the requirements. You don't say if it is one-to-one and onto, because this thing is not necessarily a mapping. So one and ontoness is with respect to mapping. So if it is both one-to-one and onto, you are referring to mapping, but we don't have that type of thing here. But what we have is having another morphism that if I compose, I get one. So which means like if you are in this category here, a natural number will be an isomorphism if there is another natural number that if you compose with it, you get what? The identity of the of the of the morphism, the identity of the actually the identity morphism. And then the identity morphism, which one is it? It will be the the number one. The natural number one will play the role of the identity. And so therefore you can see that you don't have isomorphisms inside the set of natural numbers viewed as a monoid, where the numbers are viewed as morphisms in this construction of this category. So the idea is more general than you may think it is, but actually this is how it is generally defined. And so, but we have a small result here that the inverse of F, a morphism, if you have a morphism, the inverse of that morphism is unique whenever it exists. It's not every morphism is an isomorphism, but if you have an isomorphism, its inverse is actually unique. And so we can denote it by F inverse. So this G is always unique. There is always one and only one such G. And so therefore we can denote it by F inverse. This is the proof. If you assume two of them, G1 and G2, in inverses, you see inverse is always from B to A. It reverses the arrow. Inverse is from the target to the source. And so if you have two inverses for F, then G1, by definition of composition, this will be, and by definition of identity on B, G1, and then if you apply B to B, the identity from B to B, and then apply G1, you get G1. So G1 times 1 will give you G1. So if you do this composition, you get G1. And then, but 1, since G2 is the inverse of F, 1 is FG2. But then composition is associative from the definition of category. We can associate here to get G1F, G2. But this is the inverse of F again. So I will have the identity on A times G2, but then identity on A times G2 will still produce G2. So therefore, any two inverses you pick, they will turn out to be the same. And so therefore, inverse is unique for any actually morphism in the category. Whenever the inverse exists, it is always unique. We are not saying always inverses exist, because not every morphism is an isomorphism. But whenever it exists, it is unique up to this type of realization. And now we define the notion of diagram and commutativity of diagram. Uh, so a diagram in a category C is a directed multi-graph whose vertices are objects in the graph and whose arrows or edges are morphisms in the graph. So you just, if there is a morphism from A to B, you put an arrow. So that is it. And then the vertices are objects in the category. So any such directed graph is called a diagram in the category. And then a diagram in a category is said to be commutative, or is said to commute if for each pair of vertices A and B, any two paths from A to B are equal. So let us look at an example here. You see, this is a diagram, because in a category, in some category C, you have A, B, and C, and there is a morphism from A to B. That morphism, if S is F, then I put an arrow, directed edge, I label it F. And I have two different morphisms from B to C. One is G and one is K. And also I have a morphism H like this. So this is another diagram here where you are dealing with three objects, and then the corresponding morphisms are shown. So when do we say this diagram commutes? This diagram is said to be commutative diagram if you take any pair. If I take from A to C, now any path that take me from A to C must be equal. The composite, if I compose the resulting arrows, the result should be the same. So in other words, this will be a commutative diagram if F composed with G is the same thing as F composed with K and is the same thing as H. So G after F must be equal to K after F, and that must be equal to H. So if this whole, then the diagram is commutative, because any two paths will always get me to the same result, morphism inside the category. And likewise here will be commutative if any two paths that connect any two vertices or objects are equal. That is, when we say are equal, we mean the result of the composite. So if I compose K with G, in other words, G after K, that should be equal to F, because KG will get me from A to B, and if I go directly F, I'm also traveling from A to B in the graph. So this composition should be equal to this morphism. So if that happen, and throughout the graph, not only, you don't just check this and conclude that it is a commutative diagram, you have to check all paths. So there is another path also. Actually, this is the only path from A to B. But if you look at A to C, you have only one path. It is K, via K. And from A to D, you can either do it KH or FL or KGL. And so therefore all this composite must be the same. So if all these are equal, K after G after L, that is K after G after L, no, L after K after L, because of our notation is reversing our notation of the composition. We are saying L after G after K. So apply K first, then G, then L. And then this should be the same thing as apply F, then L. Because if you do F, L, you also travel from A to D. And likewise, if you do KH, so H after K should get you from A to D. So all this path from A to D must result to the same composites in your category in the home set. So if this is the case, and also the other one, which is from C to D, because from C to D I can travel H or GL. So if all these are the same, so we say the diagram is commutative. So in order to check the commutativity of this diagram, you have to check all these composites. GK must be equal to F, and LGK must be equal to LF, and must be equal to HK, and LG must also be equal to H. So only then you now say this diagram is a commutative diagram. That is what we mean by commutativity of a diagram. And then we see this is a language that we adopt in most of our theory, abstract algebraic theory, and even in our study of homological algebras. So the next thing is to talk about monomorphism, epimorphism, and isomorphism. So I think isomorphism should be removed here because I have defined it already in the previous slides. So, and this should prepare your mind into thinking that this is something more general than what you have learned. Because in defining an isomorphism previously in group theory, maybe we need to say an isomorphism is a homomorphism that is both a monomorphism and an epimorphism. But here, that requirement is not necessary. You don't need to define monomorphism or epimorphism before you can define isomorphism. So what I'm presenting here is the definition of monomorphism and epimorphism. So when is a morphism said to be mono, or sometimes we call it monic or injection? So this is the notion of one-to-one, actually. But you think of one-to-one if you are in a set. If you are having a set mapping, you think of 1-1. So, but you call it injection or monomorphism or monic. I think this is the mostly the terminology we are going to adopt. We'll be saying, I will just say let F be a monic, meaning it is a monomorphism, because it's actually shorter in writing. It's a short form of writing it. So we say in a category, a morphism from B to C is monic or monomorphism if for all object A in the category and all morphisms from A to B. So look at the definition. You have this morphism from B to C, and then given any object whatsoever and any morphism from that object to B, so, any two pair of morphisms from A to B, like this, from A to B you have F, and from A to B you have G, two pair of morphisms, and then this morphism is the one you are defining to be a monic. So if given any such object A and any pair of morphisms from A to B, the product U after F, meaning if I multiply F and then U, apply F then U, and the product U after G, G then U, should always imply F equal to G. So in other words, we are saying if this diagram is commutative, then F must be equal to G. So whenever this diagram commutes, then F must be equal to G. So I will just stop. I will allow you to go and look at this definition and try to compare with what you know to be injection. So because this is actually, if you are having mappings, this is actually defining, is equivalent to that definition you know of one-to-one map. So this is actually the definition of one-one mapping if we are dealing with mappings. So think about it very carefully, because if U is one-to-one, you see for all FU, you have A to B F equal to, you see, if FU is the same thing as GU, always imply F and G are the same, then this must be one-to-one. U must be one-to-one. So which means you can cancel U from the left. Right? Okay.